This is perhaps podcast number 73, and today this is the second part of the Hyperloop Aerodynamics podcast set, the second half and the final half. So if you haven't listened to podcast number 72, which is the first half, go back and listen to that because we cover a few things such as the critical Mach number and how the Hyperloop system operates. This second half, we're going to be looking at the shock structures and effects of temperature and other aspects on the drag and the operation. And to do that, we're going to look at the same paper again called Numerical Analysis or Aerodynamic Characteristics of Hyperloop System. And this is open access. Again, you can find it in the link in the description. So we looked at some of the drags, such as the pod length on the drag in the last podcast. Let's move on to the shock cell structure. So they said, as mentioned above, the geometrical features of the Hyperloop system are similar to those of conventional converging and diverging nozzles, which exhibit well-known complex flow phenomena such as choking and shock waves. So we mentioned in the last podcast that converging and diverging nozzles are very beneficial in terms of being able to accelerate a flow above the sound barrier, but with that comes some challenges. One of the most important supersonic flow phenomena, shock waves, occurs when the fluid moves faster than the speed of sound. So in other words, something that seems by conventional standards theoretically impossible because the speed of sound indicates that that's how fast the fluid can move, but it can move faster than that. They are discontinuous and difficult to control, these shock waves, rapidly changing the flow fields of pressure, temperature, and density. So the shock wave effectively acts like just a one sheet in the flow, where before the sheet you have a certain set of parameters, such as the pressure might be a certain amount, the temperature and density. Then after the sheet, it's completely different. And that's because this shockwave creates this discontinuity in the flow. And that's happens because we are pushing the fluid above the speed of sound. So the typical way of explaining this is that information cannot travel to the flow, like across this shockwave, so that these parameters cannot equalize effectively. So that's one very common way of explaining it with information propagation. And when we say information, that really means anything from pressure, temperature, or density, or whatever. We just use information as a general term, which in effect, when you boil it down, it is information of some sort. So figures 7 and 8 show the variations in Mach number and pressure with respect to the pod's speed. They say that flow velocity reaches a Mach number of 1 at a pod speed of 180 meters per second. So that's only a Mach number of 0.52. The critical Mach number is 0.52. That's really bad. Like if you were to design an airfoil with the Mach number of that, or an airplane, that'd be terrible. And really, streamlined bodies, you're not going to get a critical Mach number that low. Usually they're going to be above 0.8 or so. So really only bluff bodies, you're going to get critical Mach numbers this low. Interestingly, they say the critical Mach number calculated from equation 10, which if you remember from the first podcast, number 72, we looked at an equation that you can calculate the Mach number in one dimension based on just a few parameters, such as the Mach number, obviously, the specific heat ratio, and then there was another parameter, I can't remember exactly. But from that equation, the critical Mach number was 0.41, which is lower than the one obtained from the present 2D simulations, which was 0.52. This is good because the higher the Mach number goes, the faster you can go without incurring this shock wave and the associated drag penalty. This difference in value is because of the two-dimensional nature of the present Hyperloop study. Shock waves were observed at a pod speed of 200 meters per second at the end of the pod and became more distinguishable when the velocity increased to 250 meters per second. So that makes sense. As you increase the speed that you're going at, the critical Mach number is typically going to like the point at which sonic flow first occurs is typically going to migrate upstream, and this is what happens here. The strong shock cell structure at the end of the pod was caused by severe choking of the flow around the pod. So the pod, as we mentioned, the first half of this podcast, because you're putting it through a tunnel, you're effectively blocking off a lot of the cross-sectional area, so the flow has to go around it and accelerate just to get around it. So that's why you're going to get this choking, because the flow around this pod is now going to accelerate past the critical Mach number and even past the speed of sound, and that's when choking occurs. So in conclusion, as the pod speed increases, the pressure differences between the nose and the end of the pod increases. However, once the choking phenomenon occurs, the ratio of pressure drag to total drag gradually converges to 0.93, as we also saw in the first podcast. So let's look at figure 7, which shows the Mach number contours around pods for various pod speeds. So when we're only going at below 200 meters per second, there's almost no flow that, actually below 180 meters per second, there's no flow that's hitting the critical Mach number. So that's good. We're getting very close, but then once we hit 180 meters per second, the critical Mach number is reached, and we're getting sonic flow just at the tail of the pod. Interestingly, as we increase the velocity, we start to get this choking phenomenon, and we can see that by discontinuities in the Mach numbers, so in the speed around the pod. So at the trailing part, you can see the wake, and that's fairly continuous at the moment at 200 meters per second. But around the wake, where the faster moving flow is, you get regions of very fast moving flow, then regions of a little bit slower flow. So there's this I want to say sketchiness, but there's this non-uniformity to the flow around it, where you have really not very good mixing of the flow properties, as we mentioned before, because we have shock waves forming. Information cannot propagate through these shock waves, so the flow parameters cannot equalize. So you can't have the same flow velocity right next to each other, because there's this shock wave dividing these two parts. As you increase the velocity even further, up to 350 meters per second, which is just above the speed of sound, we start to get the wake kind of looks like a diamond pattern. So if you're familiar with a fighter jet or any jet engine, really, when you go very fast, you often get something called a jet screech. And this is a noise that is produced. And this occurs partly because of this like diamond pattern that occurs from the wake. And the wake that this shows, or this is from a jet actually, the jet has this diamond pattern. But the wake here also has this diamond pattern as well. So I'm not sure whether it's a akin phenomenon or not, but it looks very similar. And what this means is that there are certain parts of the wake now which are sonic and certain parts which are not sonic. So it's all over the place. And that's also going to not only increase drag, but also increase sound as well. And the pressure plots around this mimic these same effects. So when we got 200 meters per second, the pressure just at the back of the pod is very low in some regions, but very high, or not as high in, not as low as in other regions. So in some regions it's 60 pascals, other regions it's maybe 70 pascals, and they're very close to each other. So there's discontinuities forming everywhere. As you increase the speed, that these discontinuities occur even more. At low speeds, as we go from the leading edge of the pod and we go downstream, the pressure reduces. Okay, so one thing, I'll get to it in a second. I was going to talk about the pressure drag and wave drag, just this definition, but I'll get to it in this section next. So effects of true pressure. The target true pressure of the Hyperloop system is 101 pascals, so 1,000th of atmospheric conditions. This is because a lower true pressure corresponds to lower drag on the pod. In this study, they analyzed how the change in pressure affects the drag on the pod. Figure 9, let's just look at figure 9. I guess these show just drag plots. We'll get to them in a second. Figure 9 shows the variation in drag with pressure changes at blockage ratios of 0.36. The total drag, pressure drag, and friction drag all increase with increasing pressure, as shown in figure 9A and A to C. Interestingly, the friction drag exhibited a slightly different tendency. Generally, the friction drag increases slightly with increasing pod speed at 100 pascals and 250 pascals. However, at pressures above 500 pascals, the friction drag increases significantly at low speeds. At 500 pascals, the friction drag increases rapidly above 200 meters per second, while at 750 pascals and 1000 pascals, they produce rapid increases above 100 meters per second. So in other words, as you increase the pressure, the point at which you get rapid increases in the friction drag is at lower velocities. So if you suck as much pressure out, as much air out of the chamber as possible, you can then go faster without incurring as much friction drag, which makes sense. However, the effect of the friction drag increased at around 200 meters per second when the pressure was 500 pascals. At higher pressures, the influence of the friction drag increased significantly above 100 meters per second. The effect of pressure drag gradually increased as the speed increases. So just a few things. One, so they have some graphs that show the total drag and also the pressure drag and friction drag at different speeds for different pressure conditions inside the Hyperloop system. Interestingly, as you get to a certain velocity, these drags just skyrocket, and that's because of an increase in the friction drag and also the pressure drag. But the pressure drag makes up most of the total drag, so that's the main culprit. Interestingly, though, when you get to very high speeds, so 350 meters per second, so at that speed, with a pressure of 100 pascals inside the Hyperloop system, the total drag is only 1,000 newtons. However, when you increase it to 1,000 pascals inside the Hyperloop system, so 10 times the amount, the pressure drag is now closer to 12,000 pascals, 12,000 newtons, sorry. So more than 10 times the amount, it seems. So from what I can tell, it doesn't seem to be a linear increase. In other words, if you increase the pressure inside the Hyperloop system, the drag seems to increase not disproportionately and not in a good way, from what I can tell with these graphs. Now I want to talk about the distinction between pressure drag and wave drag. So with drag in general, as I go through actually in some of our courses on theoretical aerodynamics, which you can find in link in the description, I talk about the components of drag. So in this paper, it's a good example of how you can break down drag into different components. So the total drag is just the total resistive force on the body, but that can be broken down into the drag that's being produced from the pressure difference, the drag that's being produced from friction, or the drag that's being produced from vortices that are being created, and so on. Now, another type of drag is called wave drag, and this is, in this particular case, it has a fairly loose meaning. Like, for example, if you're swimming, if let's say you go underneath the water and you're very close to the surface, there are waves that form on the top. And this is also characterized as wave drag, but it's not really the same phenomenon in this case. But in this case, wave drag is when you get drag due to reaching the speed of sound. So you get this additional component of pressure drag. Effectively, it hides itself in this increase in pressure because of the shock wave that's being impinged on the object. So even though you can group it all together with pressure drag, you can actually divide the pressure drag into the, I guess, non-sonic pressure drag part and then the wave drag part. So you can divide this even further. How you would do that is kind of up to the researcher. You can specify what you would do, but one way would be just to look at the additional drag increase due to the increase in velocity because of the shock. So in this paper, they're just talking about the pressure drag in total, but that can be divided into the wave drag plus the traditional pressure drag. The wave drag just hides itself in the same general physics as the pressure drag in terms of changing the pressure on the surface, which all forces is propagated through the pressure on the surface. Like even friction drag, when you have friction drag over an object, that's going to result in different pressures on the surface, and that's when you get drag. That's when you get a force on it. You can't have force without pressure on the surface. So all different types of drag, all different components of drag, they will affect the pressure on the surface. But because we can decouple them better, we can understand what the different components are in terms of their magnitudes. So the pressure drag in total in this case is not just the wave drag, but also the traditional pressure drag idea. So I wanted to cover that there. So let's move on. To confirm the above phenomenon, where they examine the term as tensity, so the above phenomenon was when you change the pressure, the drag changes accordingly. So figure 10, let's look at figure 10. They have the term as tensity at different points along the Hyperloop system at different speeds. So which is cool. Like term tensity is very important. We've done a podcast on it and why it's important. So you can check that out if you like. So for 100 pascals and 250 pascals, the results exhibit a similar trend. The terminus tensity increased significantly at the end of the pod, but did not directly affect the pod. The reason is that the drag measured here was the mean value of the drag applied to the surface of the pod, and the terminus tensity increased at the end of the pod. However, the terminus tensity increased at the pod's surface at pressures greater than 500 pascals. At 500 pascals, the terminus tensity on the surface increased significantly at the center of the pod at speeds of 200 meters per second. In addition, the terminus tensity increased at the back of the pod at speeds of 100 meters per second at pressure of 750 pascals, and significantly increased at all pod speeds except for a speed of 50 meters per second when the pressure was 1000 pascals. This increase in terminus tensity and friction drag on the surface of the pod were caused by increases in the tube pressure, density, and Reynolds number. So what does that mean in English? Okay, so they've covered a lot here. What they're saying is as you increase the pressure, as we know, what we've seen in other situations, the terminus tensity increases at even lower speeds. So what that does is it increases, for example, the friction drag. So by increasing the pressure, the actual pressure inside the Hyperloop system, you're going to get a lot more drag because of the friction drag at lower speeds, and that's because of the terminus tensity being changed. So in figure 10, I should just probably cover how turbulence density does change things. In the podcast that I mentioned, I go into that as well, but I'll just mention it briefly here. So the boundary layer and just the flow in general, its uniformity and behavior is very heavily influenced by the turbulence density. So the greater the turbulence density level, the lower the velocity you can have and still have a turbulent boundary layer or a turbulent flow. And that's because the turbulence density is effectively just how non-uniform the flow velocity is. So you might have one point where the velocity might be 20 meters per second, right next to it might be 40 meters per second. So that's a huge difference. And that's going to create a very big disturbance in the flow, which can trigger turbulence or a breakdown to turbulence. So that's how turbulence density can affect the flow in a nutshell. If you want to know more, check out the other podcast that I mentioned. So in figure 10, let's look at figure 10 again. This was the turbulence density as we go downstream of the pod at different pressures. They say turbulence densities at the frontal region of the pod started to increase at a pod speed of 300 meters per second and a true pressure of 500 pascals. This is because of a strong turbulence occurring near the true wall at the front of the pod. Such turbulence was generated due to the relative difference in flow velocity at the wall and near the wall. So you have the flow that's being accelerated around the pod, and this is going to create a lot of turbulence because it's not going to accelerate uniformly. And also with the presence of shock waves, it greatly complicates things again. At a relatively low pod speed range, flow velocity at and near the wall were the same. However, at relatively high pod speed ranges, this difference became greater, causing stronger turbulence. Again, because as you have different parts reaching sonic flows and experiencing different pressures in that. The frontal region of the pod is affected by compression waves and choking. These phenomena have a significant impact at high pressure and high speed conditions, resulting in an increase in pressure at the front of the pod. This accelerates the relative velocity difference between the true wall and near wall flows at the frontal area of the pod. Now, one really cool thing about shock waves is that, so we're talking about the walls and how the flow is going around the pod and it's near the wall. And when you reach this critical Mach number, you're going to be getting sonic flow and shocks associated with that. One cool thing about walls is that you can bounce a shock wave off a wall, and it might seem a bit strange that you can do that, and it actually does happen naturally, because the shock wave, when you think about it, is this discontinuous point in the flow, and that means that this discontinuous point has to stay coherent as it hits the wall and rebounds off. So it's really strange, but it does happen. And if you actually know what the angle of the shock wave to the wall is, and assuming the isotropic properties, which means that the flow stays about as chaotic as it was beforehand throughout the entire ordeal, you can calculate the angle which the shockwave will bounce off of. And I've done a CFD simulation on that on our YouTube channel. I think more than one, actually. So let's move on. So now we get down to brass tacks. The energy cost to overcome drag. This is what it all comes down to. How much energy and how much money does it cost to overcome the drag with different conditions? So they say an additional simulation was conducted as a control case whereby the pod traveled in atmospheric conditions without the tube. The aim of this simulation was to determine the economic efficiency of the near vacuum tube installation. So in other words, how much cheaper it is to run a Hyperloop compared to a regular train just going through the world. The results were compared with a Hyperloop system under a true pressure of 100 pascals and identical pod speeds of 30 meters per second, with an assumed travel time of 15 minutes, traveling approximately 315 Ks. That's pretty awesome to be able to travel 350 Ks in 15 minutes. So the results show that for the control case, which is just the regular train going through the world, it generated a drag of 407,000 newtons and required 35,000 kilowatt hours over the entire trip, whereas the Hyperloop system had a drag of only 1,000 newtons and required only 96 kilowatt hours for the entire trip. So if you were to look at the electricity costs for the control group, it'd be $7,000 for that entire trip. For the Hyperloop, it's only $20. So that's pretty sweet. So, and this is assuming that fully efficient usage of the energy to overcome the drag. So experiments and tests conducted at the Korean Railway Research Institute concluded the initial cost of vacuum creation and maintaining a specific vacuum pressure when installing a steel to be inexpensive. The results show that the energy cost required to overcome the drag is approximately 350 times greater in the control case than in the Hyperloop system under a tube pressure of 100 pascals. Hence, the near vacuum tube greatly reduces the energy cost for high-speed transportation, not to mention that you can actually go faster as well. So you can get to where you're going even quicker than our modern equipment, like in podcast number 1, so podcast number 72, the first half of this series. We're talking about the high-speed railways in Japan, and they can reach up to 580 k's per hour, whereas the Hyperloop system goes well above 1,000 k's per hour. So it's not only cheaper, it's better. So let's look at the effect of temperature. So the Hyperloop system will be operating at different temperatures. The change in drag resulting from changes in temperature has not been considered in previous studies. In fact, changes in temperature are an important factor in the transonic speed operation of the Hyperloop system. Why is that, you ask? Well, the reason is because the temperature affects the Mach number. So in podcast number 72, the first half, we had the equation where the Mach number equals the square root of gamma RT, where gamma is the specific heat ratio, the specific heat constant ratio. R is the gas constant, which is 287 for air, and the gamma is 1.4 for air, below hypersonic speeds, I should say. And temperature is whatever you want, maybe 300 Kelvin or 280 Kelvin, whatever. So the Mach number is equal to that. And so if you increase the temperature, the Mach number will also increase the speed of sound. And so that means that if the temperature increases, you can actually go faster without having a higher Mach number, because the speed of sound is higher. So the tube temperature affects the parameters such as speed of sound, density, and viscosity, and that has a significant impact on the drag. So in figure 12a, the total drag applied to the pod decreases as the temperature increases. And that's because the pressure drag decreases because the speed of sound is higher, which means the Mach number is lower that you're traveling up, which means you're not going to be getting to the critical Mach number, or at least less of the pod will be in the critical Mach number range or in supersonic speed. So you get a reduced wave drag and reduced pressure drag because of that. So the change in drag according to this temperature change is only significant for the pressure drag, though, with the friction drag relatively unaffected. It can be seen that the ratio of the total drag to the pressure drag tends to converge above 300 meters per second for higher temperatures. So we saw this for other parameters in the first half of this podcast series. Once we got above 250 meters per second, for some reason it wasn't for some reason, I'll cover it in a second, the amount of the total drag that the pressure drag makes up just plateaus to about 93% or something. And the friction drag continues to rise, though. So they say that, let me see where we are. Hold on a second. Okay, so they say that this convergence is because the severe choking was delayed by the increase in the tube temperature. As a result, the drag decreases as the temperature increases. However, the increase in temperature outside the pod may lead to increased energy consumption to maintain the pod's internal temperature. Considering the small differences in the drag caused by temperature changes, it is relatively inefficient to increase the tube temperature as a means of reducing. Okay, so in conclusion, let's sum up both of these podcasts here. First, as the blockage ratio increases, so the Hyperloop pod takes up more of the tunnel area, the drag on the pod becomes greater because of the smaller critical Mach number, because the flows accelerate more to go around the pod, which means that it's going to be hitting sonic speeds at a lower pod velocity. Second, as the pod speed increases, the overall drag increases, which makes sense. For a tube pressure of 100 pascals, the drag increases from 7.42 newtons at a pod speed of 25 meters per second, which is nothing. It's like less than a kilo of force. It's like a pound force. It increases to 1,000 newtons at a pod speed of 350 meters per second, which is still almost nothing. I mean, it's like 100 kilos force, 200 pound force. It's nothing. I can bench way more than that. But anyway, enough about me. In particular, the drag significantly increases when the pod reaches the critical Mach number. Strong shock waves begin to occur at 200 meters per second for blockage ratios of 0.36, and at 225 meters per second for blockage ratios of 0.25 near the end of the pod. Above this speed, the flow around the pod becomes severely choked at both blockage ratio values, and the ratio of the pressure drag to the total drag converges to its saturation level. Third, changes in the length of the pod do not significantly affect the total pressure drag, but strongly affect the friction drag. Fourth, the true pressure and drag show a proportional relationship. Specifically, the friction drag increases rapidly as the true pressure increases. This is due to the more energetic turbulence at high pressure and high density flow, which is confirmed by the enhanced turbulence density along the pod surface. And finally, high tube temperatures increase the speed of sound, thus reducing the Mach number for the same pod speed and delaying the onset of choking. This reduces the aerodynamic drag, and these results are applicable for the fundamental design of the Hyperloop system. So that means if you run the Hyperloop on a hotter day, it will be cheaper than on a colder day. So that's in this podcast. Make sure to like, subscribe, and tell your friends about it if they're into this thing as well. And if I mentioned the courses that we do for theoretical aerodynamics to get better aerodynamics, or if you also want to do CFD courses to get better at CFD, we have them too. Link in the description. And also, if you do experiments or you have CFD that you want to validate with experimental data, you need to make sure you measure the density of air, because as we've talked about throughout this paper, it does change with different with different atmospheric conditions. And on a regular day, it changes by 2 to 4%, and that's not even like on a stormy day or anything. It's just a regular day. And between weeks and months, it changes more than that. So we make an instrument to accurately measure the density for you, and it gets rid of that error, which propagates everything, including the Reynolds number to Joule numbers to whatever, forces and flow physics. Podcast 54 goes through that, and this instrument is really easy to use and link in the description. So make sure to get one for yourself and make your experiments better and your CFD easier to validate. I'll see you in this podcast. Peace out, amigos.